we have seen that an inner product space is basically a vector space with an inner product defined on it. And an inner product is basically a generalization of the dot product of three-dimensional vectors. We have also seen that the dot product helps us to obtain the angle between two vectors and to define the perpendicularity of vectors, etc. Now, given a function from v cross v to k, k is either r or c. In order to check whether that function is an inner product or not, what you have to do is, if you want to say that it is an inner product, you have to prove all these properties. And if you want to say that it is not an inner product, then you have to produce an example showing that one of these properties doesn't hold for that particular function. Now, for two-dimensional vectors, we know that two vectors are perpendicular if the dot product of the vectors is equal to 0. So that has been extended to the case of an inner product space, and we define two vectors, orthogonal vectors, if the inner product of these two vectors, say u and v, is equal to 0. For example, in R2, we say that the vectors 1, -2 and 2, 1 are orthogonal because the dot product between them, that is the inner product, so that is 0 because 1 into 2 plus -2 into 1 is equal to 0. In CAB, we can say that two functions are orthogonal if integral a to b f of x into g of x bar dx is equal to 0. For example, in c minus pi pi, we can see that the functions sin x and cos x are orthogonal because if you integrate minus pi to pi sin x into cos x, the answer will be 0. And so in any inner product space, you can say that two vectors u and v are orthogonal if their inner product is 0. Now, when do we say that a collection of vectors is orthogonal? A set v1, v2, etc. vn is said to be an orthogonal set if the inner product of any two different vectors of that collection gives you an inner product equal to 0. This is not the dot product, it is actually the inner product. That's a mistake here. So inner product of vi comma vj is equal to 0 whenever I not equal to j. For example, I consider three vectors in R3 as 1, 0, 1, 1, 0, minus 1, and 0, 1, 0. Then if you take the inner product of the first and second, then you get 1 into 1 plus 0 plus 1 into minus 1, that's equal to 0. Now second and third will give you 0. First and third also will give you 0. So this collection is an orthogonal set consisting of three vectors. Now in a three-dimensional case or two-dimensional case, the length of a vector can be seen to be the root of the dot product of the vector with itself. That is, length of u is equal to u bar dot u bar all raised to 1 by 2. That means root of u bar dot u bar. Now that has been extended to the case of inner product spaces, and in the case of inner product spaces, we can say that the length of a vector u, this is small u, that is equal to inner product of u with u itself. That's a positive number according to our first assumption. So that number you take and its square root has been defined as the length of the vector. And for example, in R2 you can see that inner product of the vector u with u will be giving you a square plus b square, and its root will be giving you the length of the vector a comma b. Okay, and if you go to three-dimensional geometry, you can see that the length of a1, a2, a3 is root of a1 square plus a2 square plus a3 square, which is nothing but the inner product of a1, a2, a3 with itself. As in the case of three-dimensional vectors, a vector can be normalized or made into a unit vector by taking the product of that vector with the 1 by length of the vector. So the length of this is going to be 1. Now we define the concept of orthonormality of vectors. A collection of vectors is said to be orthonormal if it is orthogonal as well as normal. What we mean by normal? Normality implies that the length of the vector is 1. And orthogonal means the inner product of two different items is equal to 0. So a collection of vectors v1, v2, etc. vn is said to be an orthonormal set if the inner product of vi with vj is equal to 0. That makes it as an orthogonal set, and every vector should have length equal to 1. That is, length of v1 should be equal to 1, length of v2 equal to 1, etc. length of vn equal to 1. Okay, so in the previous example, you can see that this collection, even though it is an orthogonal collection, it is not orthonormal. Why? Because the length of this first vector is root of 1 plus 4, that is root of 5. And the second vector is also having length equal to root 5. So these two are not orthonormal vectors, they are orthogonal vectors. Now how to make them as orthonormal is simple. You just divide the first vector by 1 by root 5 and second vector also divide by 1 by root 5. So so the first vector become 1 by root 5 comma minus 2 by root 5 and the second vector becomes 2 by root 5 comma 1 by root 5. That's an orthonormal collection. Similarly, this vector is having root 2 as length and second vector is also having root 2 as length. Third one is a unit length vector. An example for an orthonormal set of vectors is given by 1 by root 2, 0, 1 by root 2 and 1 by root 2, 0 minus 1 by root 2, 0, 1, 0. That's the orthonormalized collection obtained from this orthogonal set. You can see that 0 vector is orthogonal to each vector, that is 0 is orthogonal to each vector v. This is because inner product of v comma 0 can be written as inner product of v comma 0 into something. 0 into 0 itself is fine. Now this 0 is a scalar, it will come out, right? So this will be equal to 0 into inner product v comma vector 0. This is the number 0, whereas this is the vector 0. So 0 into anything is equal to 0 because this is a scalar. So 0 vector is orthogonal to any vector. But 0 vector cannot be made into a unit vector because length is equal to 0. So you cannot divide by 0. That's why. Now you can see that orthonormal vectors are always linearly independent vectors. Suppose a collection v1, v2, etc. vn is an orthonormal set. Then we know that inner product of v1 comma v2 is equal to 0, v2 comma v3 is equal to 0, etc. In general, inner product of vi comma vj is equal to 0 and the length of va is equal to 1. That means length of vi square is also equal to 1. That means inner product of vi with the va itself is equal to 1. So how to show that it is linearly independent? You take a linear combination c1 v1 plus etc. plus cn vn and put it equal to 0 and show that there is no connection between the vectors. That means by showing c1 equal to 0, c2 equal to 0, etc. cn equal to 0. To show this, what you do is you take the inner product of c1 v1 plus c2 v2 etc. plus cn vn with the v1 on the left side. So that should be equal to inner product of 0 with the v1, right? But 0 inner product with v1 will give you 0. Now the left side can be written as the c1 into inner product of v1 v1 plus c2 into inner product of v2 v1 plus etc. plus cn into inner product of vn v1. Now you know that since the collection is an orthonormal collection, these different elements will have their inner product equal to 0. So all these inner products will be 0. So that all these terms after the first term will vanish, whereas the first term gives you c1 into inner product v1 v1, but inner product v1 v1 is equal to 1 because length of that vector is equal to 1. So what you get is c1 equal to 0. Now to get c2 equal to 0, what you have to do is instead of taking inner product with v1, you take inner product with the v2 and you get c2 equal to 0, etc. You can show that all the scalars c1, c2, etc. cn are becoming 0. Whenever the linear combination is 0, all the scalars are becoming 0. Therefore, the collection is linearly independent. Thus, you can show that a collection of orthonormal vectors is always a linearly independent collection. But the converse is not true. Collection 1, 2, 2, 1. This is linearly independent. This collection is linearly independent, but it is not orthogonal. It is not orthogonal because the inner product is not equal to 0. However, from a given linearly independent set, you can always create an orthogonal set. Linearly independent set will give you an orthonormal set. You can create such a set. And this is done through a process called Gram-Schmidt orthonormalization. And that we'll discuss later. Thank you.